if you have a website and you don't use Cloudflare, it's very very bad. You should definitely use it. Like all Cloudflare employees start from Cloudflare users, so they start using Cloudflare, then come to work with Cloudflare. Okay, and also like before we start talking about Linux kernel Keystore, how many of you actually know that the Linux has a Keystore? Oh, a couple of people, yeah, more more than I expected to go. So a little bit about myself. I do Linux at Cloudflare. I'm interested in system security and performance, and I also enjoy low-level programming, kernel drivers, bootloaders, other scary stuff written in C. I would also like to mention I'm probably a fugitive programmer nowadays because since last year, I think, USA and NSA banned using C and C++ in important organizations, right? Probably all of you there, like on other events, you can say like, oh, like all of the attendees are mostly safe, but here is like a C, C++ conference, so we're all fugitive programmers now. And why did they do? They actually, well, they want to organizations to adopt memory-safe languages when possible, right? And bolster protection through code hardening, blah, 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 blah. So you can read the press release here. And this is kind of relates to the talk. So let's talk about application keys in memory. Before we go to the application key specifically, let's revise the concept of Linux or any operating system address spaces, right? So imagine you have like several processes running on your system. So most likely you're using some kind of operating system, right? So you have several processes. So what's inside the memory of these processes, right? So you have your main logic, well, main functions and other code you wrote. Yeah, you probably didn't write all the code yourself, so you also may have like some libraries loaded into the process address space. You also have some data section where it's constant data or mutable data. Basically, it's in the data set, like global variables, whatever. And of course, you have a stack or several stacks if you use like a multiple threads. Yeah, and like every process is like that, right? And this is all user space where your program runs. You also have your operating system kernel, which has a dedicated kernel space, and there it's kind of like similar thing, right? You have the core code, which the scheduling, IPC, and all the other stuff that the operating system needs to implement. You also have static and dynamic data in the kernel, like global variables, constants, etc. Right? You have the device drivers, obviously, and of course you also have one or more stacks because you can have kernel threads, and the kernel has its own stack, which is considered actually a limited resource. And the concept around the operating system address space is that, like, within a specific address space, anything can access anything, right? You can like basically reference any address in your application, and probably, and the same thing happened in the kernel. So at least the Linux operating system kernel is a one flat address space, and this is probably why it's very important to make sure your drivers come, especially if they're third party, from a trustworthy location, because as soon as you load a driver into the kernel, it basically has access to all of your operating system address space, including the core code, static data and stacks and whatever, right? But in between the address spaces, one process cannot access the memory of another process. And similarly, all the processes cannot directly access the memory of the kernel space. So everything is separated in memory. That's clear, right? Yeah. So now let's zoom in actually into one of the processes, and let's actually zoom in into the data section. What can we have there? Well, First of all, you can have your internal state. You write your code, you have some data structures, during the course of the application, you like change some variables, etc. So this is your internal state. You can also have there in your data section user or customer data if your service or application processes some external input, so probably some customer data is there, right? And finally, what you can have there is cryptographic keys. If your application does encryption and decryption, you use SSL or whatever, or like file encryption, so probably you need an encryption key to do the encryption operation. And that encryption key will also be in your data section. Now, let's imagine that some of our code is vulnerable or malicious, right? Either the main logic or a third-party library was hacked, or they call it a supply chain attack, and that code becomes malicious. And the problem is, because it's all in the same address space, right? The whole process becomes compromised, and mainly this data section becomes compromised as well. So like the main logic or the libraries can access anything within the data section. Yeah, but if we adopt this like categories, right? We can say that not all process data is created equal. So what if application internal state is compromised? Well, what can happen? Like, well, it depends, right? So it depends on the logic of your application. If the malicious code can, for example, influence some control data structures, they can probably lead to a further compromise. But again, it all depends on your application. So if something can only read your internal state, and maybe it's not a big deal, right? Well, if user or customer data is compromised, this is a problem now, right? So who went to my talk yesterday, I mentioned about Equifax, where they had a large data leak, and it's a big problem. It's a huge problem. It was for Equifax. It's very costly. It has a bad reputation, but still, it wasn't the end of the world. They still operate their business, right? So very bad, not end of the world. Well, but if your cryptographic key gets compromised, that's probably a game over now, right? So cryptographic keys are usually tied to identities these days. So for example, especially like we all use TLS or SSL for private key representing our web resource for like google.com leaks, and anyone can be google.com on the internet. And this is a game over, right? So it's data integrity compromise, full security compromise, and total identity takeover. So this is why when we think about protecting application data, we probably need to focus on better protection for cryptographic keys and probably user and customer data more somehow. So, well, how can a cryptographic key can be leaked, right? So, well, for example, there are several ways, but typical vulnerabilities in unsafe C++. So untrusted user inputs and out-of-bounds memory access. So for example, you have some stuff written in your memory, and you may have your cryptographic key resident in memory next to your stuff. So normally your code can only read stuff, and it was designed, not designed, I would say, as someone said, your software does what you programmed it to do and not what you intended it to do, right? So, yeah, so you intended to read only the stuff, but somehow you have a vulnerability, and now it is possible for the code to go past the array bounds and read your cryptographic key. And this is what exactly happened in the heartbleed. Everyone remembers heartbleed in OpenSSL. It was like probably at one of the hardest points in the internet. And after heartbleed, actually, all the certificate authorities tested their, rigorously tested their certificate revocation, I guess. Yeah. Well, your keys may leak if you have an arbitrary remote code execution vulnerability in your code, and there is literally nothing to discuss there. If somebody can remotely control your code, they have access to your process address space, they can dump your key or change your key and do whatever they want. And one of the recent examples of this was log4shell vulnerability. Yeah. One of the common, very common ways to leak secrets or keys is buffer use. So let's consider this simple, very naive program. So we have a main function which does encrypt and then logs the result that's saying like, yeah, I've done the encryption. And it's a little bit like specially crafted to showcase a problem. And the problem here that, for example, technically these two functions have the same stack depth, right? And in the log function, we just forgot to initialize the message to 0, right? And technically, if we compile that code on a like just average compiler with no specific security flags, you will see that the logging function will leak the cryptographic key easily, right? So what happens in the thread? So we have the process or our stack. So we have our main code. We code the, well, it's an encrypt, but here it's decrypt function, but whatever. So it gets the key somewhere, puts it on the stack, then it exits, but forgets to clean up the key. And then we have a logging function. And basically that the problem here that the logging function has access to that key material, right? And that's why, and it was briefly touched on the panel at the beginning of the conference, that's why we say like, we were discussing this new cool features, mem0 explicit, why should we zero out keys when we don't need them anymore, right? And basically this example is about the stack, but same thing can happen on the heap. If you allocate a space for the key, but don't zero it out and return it to the heap, it may be possible, depending on the implementation, that some other function will allocate the same chunk and somehow accidentally access the key or leak the key. Finally, keys can be leaked by like debugging information and tools. So if our processes crash, we may get a core dump, right? And core dump is a snapshot of the whole process memory address space, and then we'll have the keys there. So yeah, so what can we do about it, right? So like, well, we can say, yeah, it's all bugs, right? Like, let's just fix all the bugs and we'll be fine, right? Let's just, like, why do we keep revisiting this every year if we just can fix all the bugs? Yeah, it's impossible to fix all the bugs, right? What can we do? Well, we probably can solve it generically for the whole data section, but what can we do? We can kind of piggyback on the idea of the address space separation and do something better for the cryptographic keys. And what we can do here is, instead, what we can break our process into two processes, right? That second process will have its own data section and move cryptographic keys there. Then we'll add some very stripped down, easy to audit cryptographic logic. And like, even though the process one may be written in C++, we can read this in some safer language, for example, to minimize the potential vulnerabilities. And we can then create a well-defined interface between these two processes. So the process one can use the cryptographic keys, but it doesn't have the direct access to the cryptographic key material, right? And we call it basically a so-called key agent model. And it was also briefly touched on the during the panel. So like, yeah, if you're handling cryptographic keys, put them in a different process, right? So a key agent model is you have two processes, main and a helper agent. So yeah, the main process doesn't have access to the cryptographic material separated by operating system address space. And main communicates with the agent through a well-defined interface to perform cryptographic operation. And main process is usually processes untrusted and tuple is network connected, where agent doesn't process untrusted and will only request through this well-defined interface and is not network facing. There are, like, who here uses SSH agent or GPG agent? So these are all examples of an agent model. So yeah, it's all well and good, but there are some drawbacks now. Like if you want to, now you're a developer, you need to develop and maintain 2 programs instead of 1. You need to design this well-defined interface between the agent to ensure it's stripped down and doesn't allow anything else than just requesting cryptographic operations. You also need to mess now with a communication channel between the 2 processes, so like Unix sockets, shared memory, or whatever IPC mechanism you want to employ. And probably you also need to somehow authenticate and enforce some access control list. So you don't want anything on your system to be accessing the agent and performing cryptographic operations. You want to somehow ensure that only like the process intended to access the agent should have access. And it's a little bit cumbersome to do. So this brings us to so-called, the official name is Linux Kernel Key Retention Service, or I just call it simply Linux Kernel Keystore. So, and the idea is quite simple. So we take this model, right, and we replace the agent process with the Linux kernel. Will it work? Yes, because kernel has a separate address space from the process. So you have the address space separation here. And what about the well-defined interface? We also have it already with the kernel. It's called system calls, right? So we have the kernel, we have the system calls, and this is all what is all the Linux kernel key retention service is about. So it stores cryptographic keys as kernel object. And initially, it was designed as a sharing mechanism, so user space can share keys to kernel services which need access to cryptographic materials, for example, disk encryption or encrypt. But it was later extended to be used by user space program to manage their keys or secrets. And the advantages are similar to the agent model, that keys are stored outside of the process address space. You have a well-defined system call interface to access and use the keys. Now, because keys are kernel key objects, they have associated permissions and access control list, similar to other kernel objects, and that does include even LSM hooks. And the idea is that like a key lifecycle can be implicitly bound to the code like siphon. So we talked about secure, like deleting the key memory securely, destroying the key when a process terminates. And surprisingly, for a kernel feature, it has really good documentation. So yeah, you can read about that. So to review what keys and Keystore is Keystore, it's like a collection of keyrings and keys. So you have the keyrings, which can contain other keyrings, and keyrings can contain keys. So it's a tree-like structure, but you may also notice that one key can be in several keyrings at the same time. So what are keys? Keys are kernel objects which contain actual cryptographic material or a pointer to it. You can read and write to the key object if you have permission, and you can use the key to perform cryptographic transformations. Keys can be different types. I will describe the types a little bit later. So it can be user, logon, asymmetric, encrypted, and trusted. And it's kind of similar to a file on a file system, but unlike the file, keys can be linked to many keyrings at the same time. So like you can have a file only in one directory, but you can have a key in several keyrings at the same time. And keyrings are collection of keys. They call it links to keys or any other keyrings. And basically, keyrings control the lifetime of the linked key. So if a particular key is not linked to a single keyring, it gets automatically destroyed and securely destroyed. Keyrings can be explicitly created or implicit. and implicit keyrings are thread, process, URL, and session. I will describe it a little bit later. They do enforce key lifetime, and they're kind of similar to a directory in the file system. So let's see like a really basic example. So I'm on my machine. I actually copy-pasted it from the real terminal. So consider this as a demo. So yeah, so I'm on my machine. I can create a new keyring and call it my ring and link it to my implicit user keyring. And yeah, and then what I can do is I can add a key there with some secret. So Hunter2 is my secret, and I can add it to my keyring. And then I can show, and I can see like which keys and keyrings I have access to. So, and you can see this tree-like structure. I have the implicit session keyring, then my user keyring, then my custom keyring, and in the custom keyring I have my key. Yeah, and also I wanted to show that like each object, like key or a keyring, is designated the unique ID, which they call a serial number. So these are serial numbers. Yeah, so, and because I have access to my key, I can read the secret. So I can access the cryptographic material. Cool so far, right? So it's very interesting. Like you can do a lot of things with it. So for example, you can do a simple secret sharing. Now we have two users on the system, Alice and Bob. And you may see that they're not connected anyway, so they're not part of a common group or anything, but still I can securely share a secret between these two users. So what can I do is, Alice can add a secret she wants to share in her own keyring. What can Bob do? Bob can create a custom keyring called from others, which is like an inbox to receive secrets from other users, right? And he will have the serial number. He can then communicate that, yeah. And Bob also needs to set permissions, which is similar to file permission, which it means that any user on the system can write to the keyring, but even not read from it. So users can write keys to this keyring. And then Bob can communicate the serial number to Alice, and what Alice can do, Alice can move her key from her own keyring to this new Bob's keyring. And then we see that Alice doesn't possess the secret anymore. So there is no user secret in her tree. And Bob now has access to the key. So Bob can read the secret, he can read the material, and this is because like Bob has access to the key now. So you can see the user secret in the Bob's keyring. Okay, so what about special keyring types? So we created the custom keyring, but there are like implicit keyrings. So there are three main types called which are bound to a process lifetime. So the session keyring, it's implicitly created by the kernel when needed, and its lifetime is bound to the current and all child process. So to the current process which requested the creation and all child processes of that process. So you have a process keyring which is private to the process, and you can have a thread keyring which is private to a particular operating thread. So which is a nice thing because, for example, if you have, let's say you have a web server which like serves several websites and you have a dedicated threads per website, you can, for example, securely store SSL private key for which website in the thread, and like you can make sure that other threads cannot easily access that private key. You also have user keyrings, which the lifetime of the keyrings is implicitly bound to a user ID. So user keyring is shared between all processes with a particular user ID. And user session keyring is very similar to user keyring. And I honestly even forgot what's the difference, but it's not very important. And even the docs say it's not very important. So probably it's true. You also have a third type called persistent keyrings. It's also shared between all processes with a particular user ID, but the difference is it's actually, the name is confusing. So when people hear persistent keyrings, they think that the key object is somehow persist on disk, which is not true. So persistent keyrings means that the lifetime of the keyring is not bound to an existence of user ID, but instead it's basically destroyed on a timeout. So you have like an object, this keyring, when you use it, the timeout resets, and if you don't use it for a while, it gets automatically destroyed. But if you again use it, like the timeout resets. So this is basically, it was designed for non-interactive jobs like cron jobs, which like come and go. So you don't have to recreate. If like you have, let's say, a cron job running every 5 minutes, need access to the secret. So you can set the lifetime of the keyring to 7 minutes, and the keyring will always be there. But if for some reason your cron job didn't run or crashed, then that key will be automatically destroyed. Let's actually see the example of session keyring and the lifetime of the keyring. So let me add a secret, my favorite Hunter2 password, which I use everywhere, by the way, to my session keyring, right? So yeah, and I can see it's there. You can see that, yeah, the serial number is here, and like I can access my secret, right? What I can do to prove that it gets automatically destructed, I can put a BPF probe on the user destroy function in the Linux kernel, which is responsible for securely destroying a key, and in a different terminal. And then here, like, so the above terminal, I'm SSHing here. So I exit an SSH session, and I can immediately see that when I logged out, because my session keyring was automatically destroyed, therefore all the keys linked to it were also destroyed, that the kernel called the user destroy function, and I can see that the serial number is my user key. It was like securely deleted, like wiped from memory. And if I re-login back, I can see I no longer have the key, and I can also see that my session keyring was recreated because the old one was destroyed. Then the system automatically created a new session keyring, but it has a different serial number. So the idea of implicit keyrings is that if you select the appropriate keyring type, you can ensure that the keys will be securely destroyed when not needed. And the nice thing about it, it happens even if the application crashes. So even if you write C++ code, you zero out memory or destroy the object in your destructors, but somehow your application crashed and destructor wasn't called, the kernel will make sure that all the key objects will be destroyed. I think this is the power feature. So let's now review the key types. So we have the user key, which we used throughout the examples, and the user key is the simplest type. So what it does is just a buffer with a secret. You can basically put it inside the kernel, and other processes can read the secret back, right? And either you can read, your process can read it, or other processes can read the secret, but if they have the appropriate permissions, because you can set permissions to disallow that. There is a so-called logon key, and the idea is that you have a secret, you put it inside the kernel, but you can never read it back. And this is the original, it comes from the original idea of sharing secrets with the kernel. So once you provide the secret to the kernel, no other process can read it back, but the kernel can use it, and it's used in LUKS or the encrypt or encryptFS. So if you have a recently modern Linux distribution, you can see, and you have encrypted disks, you can see that your keys are actually where a logon key is. So when you initialize your disk encryption, you provide the password. The crypt setup utility creates a logon key, sends the key to the kernel, and then it exits. And yeah, there is no way to read the key back into the user space. We also have like a specific asymmetric key type. So currently, kernel only supports RSA keys, but I'm actually working on patches. I have patches to extend to elliptic curve cryptography, but I'm still for some reason, they were still not accepted because I could not get hold of the maintainer. So you can put an RSI key in the kernel, and then instead of reading it back, you can, if you have access to the descriptor, to the serial, to the key object, you can request the kernel to do cryptographic operations with this key. So you can either decrypt or sign. So here is a simple example. So let's generate a simple RSA private key, right? Now we also need to convert it to PKCS8 format because this is how the kernel understands asymmetric keys. And now we can add it to a session keyring, for example. And yes, so then we can create some test data and use and ask the kernel to actually sign this data with the kernel object. So like this, the cryptographic operation will be performed inside the kernel, and you don't need to have access to the key material itself to do the signature. And yeah, and then we can verify with OpenSSL that the signature is valid. So think of it as a light software HSM inside the kernel, which is cool, I think. So using this asymmetric keys, we can actually, like, let's say, re-implement the SSH agent model fully inside the kernel without the need to run a separate agent process. And I will not present the example here, but I will refer to our blog post, which has actually a patch for that. So you can just patch OpenSSH with the patch, and instead of running an agent, you can just easily put your SSH key inside the kernel keyring, and OpenSSH process will use it to authenticate to your service. And the workflow is similar. So you do SSH add, but the key goes inside the kernel keyring, and then when you try to SSH into the system, it will not talk to the agent, so you don't have to run the agent at all. So this functionality is really useful to build like very complex key management systems, both in cloud environments and even in a fleet of IoT devices if you run Linux. But the idea itself, like in all the previous examples that we saw, we had user space taking a cryptographic material and putting it inside the kernel, right? But that opens the window of opportunity to the attacker. If the attacker can compromise the user space process while the information is there, the attacker can still grab that information. So the idea is, how can we provision the application keys without the cryptographic material ever being exposed to user space? So like we can ensure that in user space, we never saw memory with the cryptographic material. There are two more key types for that specific, called encrypted keys. So imagine you have already some key in the kernel keyring. We call it a wrapping key. So what you can do is you can take a wrapped key in user space. So it's a cryptographic material, but it's encrypted with the wrapping key. And once you put it inside the kernel will automatically unwrap it with the wrapping key. So like basically the plain text cryptographic material is only available in the kernel space. And again, if you try to read it back, you get the wrapped key again. So in user space, that key is only available in encrypted form. But here we have a chicken and egg problem. Like, how do we provision the wrapping key then? Still need to. So the way how kernel approaches, well, you can put a crypto chip inside instead of a wrapping key, and encrypted keys become trusted keys. So Linux kernel has native support for TPM for that, but technically the subsystem is quite modular. So if you're an IoT device and you have your own crypto chip, it's quite easy to write a simple driver which will expose your crypto chip as the secure device for trusted keys. And the idea is, again, you have the wrapped key, you put it inside the kernel, and the kernel will use your crypto chip to unwrap that key, right? And again, you can only read it back in encrypted form. But specifically, like for TPM, there is a disadvantage here. So what if you have a lot of keys? You need to continuously poke TPMs, right? And TPMs are not really fast, and sometimes they're not very reliable. They like break quite fast. So we can do the combined schema approach here. So let's say we have some central repository of keys, and we have a particular root key we want to provision. So we wrap that root key to a particular TPM, and then deliver that key to a particular device or a server to the kernel keyring. So we use the TPM once to unwrap that root key, but all the other keys, all the applications keys are just simple encrypted keys wrapped with that root key. So when we have an application-specific key, it's wrapped with the root key, and when we send it to the kernel, it just uses the software root key instead of going each time to the TPM. So we use the TPM or a crypto chip only once, and then all other keys are to provision a root key, and then all other keys we use like the encrypted keys. Good so far? But again, this schema has problems, right? So applications, the advantage is the application never sees the plain text cryptographic material in the process address space, but it's still up onto the applications for contacting the centralized KMS or HSM or whatever you have for secret storage to get the wrapped keys. And like developers are lazy, so I want to focus on my code, but I somehow now need to put in my code the logic how to reach the centralized KMS HSM. I need to have their like URL and points in my configuration data. I need to add code for actually communicate with this HSM, and like every interface is different, etc., etc. So it's a pain for developers. And also you have like a little administrative control of the created key object. So if even though applications doesn't see the cryptographic material, it creates the kernel key objects, and it can probably set permissions on that incorrectly, so other processes then can use it, for example. So you have to audit the code of the application that it does not only properly create the kernel key object, but also set the proper permission. And probably from KMS or HSM perspective, you need to somehow authenticate each request in application. So even though you're providing a wrapped key, you don't want to send wrapped keys to applications, wrapped keys for one application to a different application, right? So the Linux kernel key retention service, or the Keystore, provides two systems calls to manage the key objects. So one of them is add key, which we used in all the examples, so which allows you to add a particular cryptographic material as a key. So like the application is responsible to providing cryptographic material, and the payload is interpreted to the key type. So nothing is done for user or logon keys. You have to provide the plain text cryptographic material, private or public key for asymmetric keys, and encrypted and wrapped key for encrypted and trusted keys. But there is also another system call called request key. And the application, instead of like providing the cryptographic material, an application is requesting a particular key from the operating system based on a free-form string ID. And obviously, like every setup is different, the kernel cannot satisfy the request usually on its own. So the kernel can call out back to user space to a helper agent program, which can then hook into external or internal HSMs, KMS, and other stuff. And that helper program is like a centralized extension of the Keystore and can adjust key permissions, implement arbitrary security policy, etc., etc. It's a more centralized and transparent API to add keys for the kernel keys. So how does it work? So instead of adding the key directly, what if a process needs a key, it just calls a system call. Hey, kernel, give me the key, and provides its ID. So let's say it's kind of cloud app key 1. So once the kernel requests, receives this request, it creates a key object, an empty key object, like a placeholder. Then it calls out to a dedicated specific user space program, which is usually has-been request key. And that program can be modular. You can basically configure it with even several paths. So depending on which ID was requested, freeform string, you can even direct it to a different backend. Let's say if we requested a cloud key, then we direct it to the cloud HSM. So that request key contacts the cloud HSM, and the cloud HSM provides the key back to this agent, and then the agent responds to the kernel, and the kernel finally instantiates the key object inside the kernel and notifies the application that the request is complete. And now the application can use that key for its purposes, right? And again, in this schema, the plaintext cryptographic material never touched the user space application. So it's a single centralized operating system API to request key from the application. So you have no KMS HSM connection strings, no URLs, no just a freeform string ID, and it basically decouples your applications from your key management and key storage backend. So all the application needs to know, if it needs the key, it asks the operating system, right? And it's a more secure way to instantiate the keys in the kernel. So when the kernel creates this callout process, it has some operating system magic to ensure only that process and not any other process can actually instantiate that placeholder. And that callout process can perform additional security checks, check if the requesting process ID is allowed to request that key, check where it's located. You can basically code arbitrarily like security policy there. And also it's modular, it can support multiple storage backends, and you can swap backends transparently, independently of applications. So if you decide to move from cloud HSM to on-prem HSM, you can reconfigure your user space helper agent, but applications will never notice it. And then also you only have one process you need to authenticate on the backend, so on your KMS system. So you need to ensure the integrity of that process, but it's only one process, which is a centralized point of communicating with your KMS. And again, even though the request key helper program, which is provided by the most operating system distribution, is written in C, you can actually write these backend connectors in any language, Go, Python, whatever you desire, and even Bash script. So eventually, with request key, key management and distributions becomes a core service of the operating system, where it should be, and you kind of like free the applications of doing their own, sometimes very buggy key management system. I guess that's all I wanted to say today. So here are some useful links. The first two is linked to kernel documentation about the kernel keystore and some arbitrary key types like trusted and encrypted keys. You also have some man pages for key CTL utility, which we used, and we have man pages for keyrings and asymmetric keys. And finally, everything I described today and even more with a patch to OpenSSH is available in our blog post, which you can go back and read anytime you like. So thank you very much. I think we have time for questions. Yes. Should we do mic, or I can repeat? Yeah. So the question is, the features demonstrated here, from which kernel it is available? I think the basic features are available, I don't even remember, from all the older kernels. I'm not versed in Red Hat. So I only know the upstream kernels, but I can say that I think it's in for something. The idea is also we recently did add a new functionality. So previously, uh, there is also another kernel feature called Linux Crypto API, where you could use Linux kernel to perform symmetric cryptography on behalf of the application. So for example, very useful for small IoT devices. If you don't want to pull a crypto library, you can just ask the kernel to do encryption, decryption. But the problem was the same. It was not connected to the Keystore at all. So it was a separate API, and to encrypt it, you needed to put the plain text cryptographic key inside the kernel, and then you can do encryption decryption. So we recently upstreamed a patch which connects these two systems. So if you have a user key already in the kernel, you can start using it to do symmetric encryption and decryption. And that is available, I think, from 6 something. Yeah, but all the other basic features are already there for a long time, so it should not be a problem. Yes, please. Yeah. So the question, basically, if I summarize it correctly, so even though we have keys inside the kernel, we still need application to send plain text through the system calls for it to be processed by the kernel, and it's very easy to trace or hook system calls, and then the attack and process can be the data itself can be compromised. And again, I'm not sure there is a really good protection against that, but it goes back to the earlier slide I mentioned. There are several categories of data, right? So cryptographic keys are more important, and the kernel key store is all about protecting cryptographic keys, whereas of course you still need user or application data or internal data, and that somehow needs to be handled, right? But I don't think there is a good way to say that the kernel can help you with that. Mm. Yeah, yeah. The idea is for example, it's still a lot of value. Let's say not all data you send for cryptographic operation is actually secret, and the prime example is for asymmetric keys as a signing operation. So you sign the public data, but the idea is if you leak your signing key, you anyone can impersonate you and sign the data, but you can keep the key secure. And signing is a really good example of why you should use a kernel key store. So you protect your private key securely, but your data that you process with that key is public anyway. It's just you create a signature. Yeah, so the comment here is you can still modify the hash. But again, it goes back to technically, if you can follow system calls and or somehow modify the data, that means your application in general is compromised, right? So if I can modify any data in the application, I can even switch the flow control, create a unique a network socket, and send it over to myself as an attacker, right? So technically, it's possible. Any other questions there? You mean the KMS backend? Mm-hmm. So the question was, how does sbin request key is implemented, and how does it know which processes are allowed? Is that correct? So when the kernel creates this callout process called request key, it executes a binary, and it provides some information there to that binary. So it says which process requested the key, and then by having the process ID, you can technically inspect the system and do like any arbitrary policy. So for example, I can write a backend which says I only allow processes at a particular executable path to request the key, or a process even with I can hash the executable. I can say, I can verify the integrity of the executable and say, if the integrity is this hash, then it is allowed. So, and basically the idea is also that this process also receives a special key from the kernel itself, so only that process can then later satisfy that request. So if you're an attacker and spin up the same executable but externally, it will not have the credentials to like malform that request or something like that. Yeah. I mean, you are free to implement policy as you wish. So the operating system basically provides you a basic sbin request key implementation, and it's open source. You can look it up. And the way how it works is it has a configuration file, and you can say further that, for example, for a particular key type, like which starts with a cloud prefix, call that other process to satisfy the request, and you write that other process yourself, like the communication agent. For like local keys, you can say that like you can basically you can configure it to further call out to different backends, to different processes to satisfy different request key types. You can also like just prohibit some key types. You can say like nobody's allowed to request an asymmetric key, period, and it will be like denied immediately. Yes. Oh, here it's like the first it was said that the first mention of the kernel key retention service is in kernel 4.13. First 4.1.3, but my assumption is in 4.1.3 it only supports passing the keys to the kernel for disk encryption and nothing else. So user space support might not be available. So probably later kernels like 4.14 or 4.19 will have a better support of all the key types. Thank you. Any other questions? Yes. Oh, that's a great question. One thing to remember that the kernel keystore subsystem is not namespaced. So if you have a container, and you operate within the keystore, it accesses your host system's keystore. And there are some like ways and attacks where if you misconfigure the kernel keystore, so like let's say if you're running in container, they can access your host key. So you have to be very careful about that. I think I'm not entirely correct that it's not fully namespace. I do think it supports user namespaces. And yeah, there are some quirks. I haven't researched thoroughly how do you properly configure it, but yeah, you have to be careful when you're using the kernel keystore in with the containerized environment. But on the other hand, I think it's also a superpower in the sense, because let's say if you run like a Kubernetes cluster, right? So you can have container applications accessing secrets without the need for application to handle those secrets. So like you as a Kubernetes cluster maintainer can provide that secret store as a kernel key store on the host. If it's properly configured, containers can just request their secrets without the need to do like whatever the Kubernetes does, secret map or something like that. So they can do just request key and get their keys in the container. Not even get the keys, just get a handle to the keys and use it to perform cryptographic operations. So the key management, again, becomes the centralized operating system feature versus each application needs to deal with it somehow. Any other questions? Thank you very much, and have a nice day.